Hello everyone. In this lesson, our topic is linear approximations and differentials. For our learning objectives, we will describe the linear approximation to a function at a point. We will write the linearization of a given function, sketch a graph that illustrates the use of differentials to approximate the change in a quantity, and calculate the relative and percentage error using a differential approximation. First of all, let's look at our exploration. We are given the function f of x is equal to 1 over x. A. Find f of a where a is equal to 2. B. Find f prime of x. C. Find f prime of a where a equals 2. In other words, find f prime of 2. D. Find the equation of the tangent line to the graph of f at a equals 2. That is, use the formula y is equal to f of a plus f prime of a x minus a. And E, use a function value for f of 2 and the equation of the tangent line to the graph of f at a equals 2 to estimate a function value for a equals 2.1, then estimate the function value for a equals 10. Now let us see how we can take a look at this algebraically. Now, we are given that f of x is equal to 1 over x. So f of a would be equal to 1 over a, and if a equals 2, then f of 2 would be equal to 1 over 2. Part B, f prime x is the derivative of x, so we want to find a d dx of 1 over x, which we can rewrite as d dx of x to the negative 1, and that by the power rule will be negative 1x to the negative 2, so by the power rule, it's negative 1x to the negative 2, and if we rewrite it back as a fraction, it will be negative 1 over x squared. Now we want to find the derivative at the point x equals 2. So that is f prime of 2, that would be equal to negative 1 over 2 squared, that would be equal to negative 1/4. Our next step, we're given an approximate equation or equation that says y is equal to f of a plus f prime of a times x minus a. So where a equals 2, that would be equal to f of 2 plus f prime of 2, x minus 2. And so plugging in numerical values, that would be 1/2 plus negative 1/4 x minus 2, because the plus minus gives a minus. We just write 1/2 minus 1/4 x minus 2. So that is our equation. Then for part F, we want to use this equation here to estimate the value at a equals 2.1. So what we will do is we will replace the x in this function by our 2.1, so y is equal to 1/2 minus 1/4, 2.1 minus 2, and then give you a calculator value there, which is 0.475. Okay, and then for a equals 10, we plug in 10 where x was, so we get y is equal to 1/2 minus 1/4, 10 minus 2, and then that will give us on our calculator negative 1.5. And so in the last part, in part F, we want to say whether or not the estimates are good or bad. So in order to determine whether the estimate is a good approximation or not a good approximation, we want to find what is your f of the real value. So f of 2.1. So we know that the estimate at a equals 2.1. So the estimate was 0.475, and then the true value would be 1 over 2.1. Then we convert that to decimals, and that would be about 0.47619. So, just matching the parts, you find that this is pretty close. So we say it's a good approximation. It's a good approximation because it's pretty close. Alrighty, so for the estimate at a equals 10, we say it's not good because the real function value, it is not close. It is not close. So we say it's far from the real function value. Why? Because the estimate was negative 1.5, but the true value is 1 over 10. That is 0.1. So that is kind of a bit far. So we say it's not really the greatest estimate, or it's not a good estimate. Okay? This is 0, that's negative 1, so it's kind of a bit way out. I'll give some definitions to what we had just learned. I want to give some definitions. We want to talk about, what kind of words can we use. We made a new function, a linear function, from our activities there. And this linear function is called a particular name. In general, for a differentiable function f, the equation of the tangent line to f at x equals a can be used as approximate for f of x for x near a. Therefore, we can write f of x is approximately f of a plus f prime of x minus a for x near a. All right, so this f of x is a real function value. This other part gives a linear function. So what we're doing, we're taking this linear function as approximate for our, usually it's a curve, most times a curve. So we call this linear function a special name. We give it a letter L, capital L of x is equal to f of a plus f prime of a times x minus a. We call it the linear approximation or the tangent line approximation of f at x equals a. This function L is also known as the linearization of f at x equals a. So we are linearizing a function, or we're trying to make a curve take on the values of a line at a near point, okay? So we're going to look at what this looks like graphically. So graphically, this red curve, when we graph this using Desmos.com, this red curve here is the graph of the function f of x is equal to 1 over x. F of x is equal to 1 over x. You notice the f of 2, if we did f of 2, is 2 and 0.5. But what we want to notice here is that when we take the tangent line at 2, which we call our L of x, right, or f of 2, here it's written as g, but it's really officially L of x. F of 2 plus f prime of 2 times x minus 2 is this green line right here. What you will notice is that very close to the point x equals 2, the curve and the tangent line are pretty much exactly the same values. That is like right from about here to all the way out of here. They're pretty much exactly the same values before they start opening up. So 2.1, 2 point up to about 2.2 there, about 1.9, so 1.9 to about 2.1. Pretty much lies exactly. So 2.01 will be pretty close approximation. But if you go to, let's say, where x is equal to 10, If we zoom out to where x is equal to 10, then notice there's a big difference right here between where the curve is and the tangent line is. The red curve and the green line is a big wide space, so that's not really a great approximation. So that is why for x values near our function or tangent line is a pretty good approximation. So that's what our definition was talking about. So let's do one more example of this idea. Consider a function f of x is equal to radical x. Find the linear approximation of f of x at x equals 9. Use this linear approximation to approximate the value of f of 9.1. So here we're going to use our idea. So f of x is equal to radical x. Right? So I want to find f of 9. F of 9 is equal to radical 9. So that would be equal to 3. Then I want to find f prime of x. F prime of x would be equal to d dx of radical x. And that's rewriting or radical x d dx of x to the 1/2. And so the derivative of x to the 1/2 by the power rule, that's 1/2 x to the negative 1/2. And rewriting that as a fraction, that'd be 1 over 2 radical x. Right? So the f prime of 9 will be 1 over 2 radical 9, be 1 over 2 times 3, be 1 over 6. So that's prime of 9 will be 1 over 6. Okay? So then we want to find the L of x function. We want to find the L of x function. So then your L of x in that case, your L of x in that case, L of x would be f of x plus f prime of x times, well, let's do L of a. Let's do L of a right here, x minus a. And so at 9 it's going to be 3 plus 1 over 6 x minus 9. 3 over 6 x minus 9. So we want to use this to estimate, f of 9.1. So what we will do is plug in 9.1 for x, plug in for x in the L of x function. And so f of 9.1, our approximation for that will be 3 plus 1 over 6 times 9.1 minus 9. It would be like 0.01 or something like that, 0.001. So that would be about 3.0167. So that is our approximation for 9.1, for the f of 9.1 using. And based on what we said or what we saw on our graphs for previously, we can tell that because 9.1 is pretty close to 9, somewhere pretty close to 9, then this would be, you know, a good approximation, for the f of 9.1. Thanks so very much for watching this video. Remember to like, subscribe, and see you next lesson.